Good afternoon, everyone, and welcome online for this new webinar organized with Plasmabound. My name is Benjamin Debucher, and I'm the Head of Events Program for JEC. Thank you for joining us today. Today's webinar is Advanced Composite Bonding, Plasmabound's CPA surface preparation technology. In this webinar, you will discover the methods to improve adhesive bonding of fiber-reinforced polymer composites, both improving bond performance and reducing operational steps in achieving these bond improvements. The presentation will review the benefits and pitfalls associated with current process and technology application, and will subsequently focus on Plasmabound's offering to this critical area, enabling the broader adoption of these lightweight materials into a greater range of markets. For those who don't know, Plasmabound is an Irish deep tech technology company providing license access to transformative technologies in automotive, aerospace, space, and many other sectors. Plasmabound CPA directly supports the EU Green Deal's objectives, specifically for sustainable manufacturing, but also promotes circular economy goals through seamless integration of recyclable composites. The technology uses atmospheric plasma to deliver specific energies to the surface of a lightweight composite material in such a manner that causes the polymer to sublimate and leave new surface for bonding. The net result is non-destructive removal of polymer, revealing virgin, undamaged, and chemically activated polymer ready for bonding. This process is controlled by Plasmabound such that predetermined depths can be achieved, and this can involve revealing undamaged structural fibers should the customer desire to act as an anchor for subsequent adhesive application. To present this great technology today, we will be hearing from Nick Barry, the co-founder and CTO of Plasmabound. Nick is the inventor of the Plasmabound technology CPA. He was awarded his PhD from the University College of Dublin and is a process development and new technology introduction specialist with 10 years of experience in R&D. We will be hearing also for Conor LUTTRELL, the R&D manager at Plasmabound. So Conor is an experienced research engineer with a demonstrated history of working with composite material in academic and industry-based projects. And he is skilled in composite processing, non-destructive testing, mechanical testing, and composite repair. And last but not least, Nick and Conor will be joined by Sebastian Wiskamp, the technical director of the Thermoplastic Composite Research Center in the Netherlands. Sebastian acquired his master and PhD grade with research on process-induced residual traces in thermoset and thermoplastic composites at the University of Twente. Sebastian worked then at Tencat, now Torre, Advanced Composites, where he spends 5 years in R&D on aerospace-grade thermoplastic composites, and then moved to business development, where he explored the use of thermoplastic composites for the automotive market. In 2015, he joined the TPRC as a business developer, working on short-term projects for both the aerospace and automotive industry. And since 4 years now, Sebastian is responsible for TPRC's long-term research projects, mostly performed by PhD candidates, in his role as technical director. Before starting the presentation, I would like to remind the audience that you can ask your question in the question tab that you can find on the bottom right of the screen. And please feel free to ask your question from the beginning as the question comes to your mind, and we will make sure to answer all the questions at the end of the webinar during the Q&A session. You can also upvote the questions from other participants if you find their question interesting to be asked to the speakers. As usual, I recommend to be connected through cable wire rather than Wi-Fi. And in any case, the webinar is being recorded, so you'll be able to view the entire program again later on gccomposites.tv. So it's now time to discover how to improve adhesive bonding of fiber-reinforced polymer composites thanks to Plasmabound CPA surface preparation. Nick, welcome online. It's a real pleasure to have with us today, and the stage is now yours.
Thanks, Benjamin. I pretty much finished it there. Really, you did a good job. Don't really need to give my presentation anymore, but I will anyway. Just to say thank you everyone for joining us, and good afternoon to my European colleagues. Good morning to those calling from the Americas, and to everyone else. I hope you're having a good day. In today's webinar, we are going to cover advanced composite bonding, but I'm also going to pare it back a little bit and try and give you some background as to why we look at these things and why they're of interest to us. Then I will also explain a little bit of what Plasmabound offers in this space. So to give you a little overview of the presentation today, essentially we're going to look at an introduction, explain who we are a little bit more, then look at FRP joining, the simple background, and then joining problems that are associated with the industry, and then also look to Plasmabound's issues, or what Plasmabound would see as the issue of joining problems. And then the CPA process itself, explain it and give its unique selling points, and explain where it can really find benefits for its customers and anybody who adopts it. Then TPRC, as Sebastian is going to show a case study where we'd worked in an independent study together. The findings from that study being TPRC's side. Then highlighting our interest in collaboration with companies and anybody who's on this call, how you might mechanize that method or how we might be able to work together. And then finally, we'll summarize what was covered in the presentation today. So first of all, thanks Benjamin for the introductions, but just to give you a bit more insight into who I am. I'm Nick Barry. I am the co-founder and CTO of Plasmabound. My background is mechanical engineering, and I have a PhD in surface engineering, where I focus on the surface phase of a material rather than the bulk phase. But my job is to allow the bulk phase to do its specific job in a given environment or scenario, so that it can work in particular applications. Joined with me is Sebastian Weiskamp. It's a technical director of TPRC, and I'll leave Sebastian speak for himself and TPRC later in the webinar, where he will take over and give an explanation or discussion of how we'd worked together in the past. Then Conor is also on the call. So Conor is Plasmabound's R&D engineer, and he will answer some of your short questions that you might have during this presentation in the chat function. But he has an extensive experience in composite processing, non-destructive testing, and mechanical testing. And so he's a kind of key member of the team within the Plasmabound ecosystem. So who is Plasmabound? We're based in Dublin, Ireland, inside the EU. We're a spin out of University College Dublin, where I got my PhD, and also a spin out of ICOMP, which is the Irish Centre of Excellence for Composite Manufacturing and Processing. We're research focused, and that is because of the people we hire, and specifically because of the management team that we have. We are research focused, but we also are commercially centered. So we try and take what has been done within the academic environment or institutional environments, and we take the knowledge and understanding of how to apply that, and we take it into the commercial sphere. So you'll see quite a bit of that today discussed. We have 13 employees and growing, and we've had private investment to date of 4.2 million. So we've been quite fortunate up until now. So what is joining? Well, fundamentally, joining traditionally is considered bringing together of two parts or more and fixing them mechanically to ensure mechanical continuity occurs across the entire assembly. What does that mean? If a force is applied on one side of the assembly, the other side has a restorative force. So essentially, the two parts stay in contact and they allow stress or strain to travel across them. There are secondary functions to joining: electrical conductivity or continuity, and also thermal continuity. But the mechanical remains the primary function or reason. There are three chief methods of joining in FOPs and structures. One of them is a more modern method, and two, which are mechanical fastening and bonding, are a very traditional method, whilst welding is a more modern or a more applied method, and it's specific to thermoplastics. If we look at mechanical fastening, well, it involves the use of a dissimilar material, usually a metal, bolt, or rivet, to act as a fastener and to isolate the opening forces sometimes experienced within a composite. And these are often or sometimes applied with an adhesive as well to fixate the joint. There is a trend away from this method due to the stress riser effect with in-plane shear when it's applied. The second method, bonding, which is just bonding with an adhesive or a solvent, It involves the use of an adhesive or solvent to join two materials, often requiring a treatment to some extent on one or more of those materials if those materials are dissimilar, so that the adhesive is able to bond to both sides. And then finally, welding, a method used primarily for thermoplastic joining and involves the melting of a surface of a thermoplastic material and controlling the cooling to ensure a suitable crystallographic structure is maintained at that bond joint structure. So it creates essentially one part out of two. The focus of this presentation is the adhesive element that we're discussing here, so the one in the middle. However, we are eager to engage with thermal welding activities as well as a technology. So, what are the problems that industry see? Well, the main one is, and nobody wants to see it, recalls due to joint failures. It equals a loss in revenue, but in some instances, even more damaging is a decline in the brand confidence through public recall programs. And this is due to a joint failure, a small component that came away from another. An example is displayed here, and it is Tesla, and loads of people like to use Tesla or other big brand names at the moment to explain a point. But the main point I would make about the Tesla issue here is they weren't overly concerned about the cost of even recalling these 9,500 cars. It was the cost to their cap that really hit them. They dipped during the day, and the overall cost of that company, of Tesla, finished lower at the end of the day than expected just because of this announcement. And this is what the industry sees. It's the fear of a recall or an event which will put their brand or their name into repute. However, because I'm not technically in that industry, but in a different industry, which is the industry associated with surfaces, what I see when I see a bond joints issue is typically most people will see 3 components, but in reality, I see 5. There are 2 common interfaces, and these are key in the performance of a bond joint. While substrate and cohesive failure are acceptable sources of failure, which are defined by the 2 components that are the 3 components that everybody sees when they look at a bond joint, it is often the situation that the last or the common interface is the reason why a recall will occur. And in the case of Tesla, it is this situation where the common interface is causing a failure. The primer is missing, and essentially the adhesive was coming away from the substrate. This can often be avoided by design choices and/or process or material selections, but they need to be known early, before you've put things together and discovered that there's a failure going to happen in a number of years' time. So what I'm really trying to say or get across in this slide is the common interface is key when it comes to the performance of an adhesive to a material. And in particular, it will be the focus of this presentation. No surprise, we're a pre-treatment technology. Of course, we'd be interested in the common interface. So when we talk of a common interface, one of the key properties of an interface is its surface free energy. It quantifies the energy available at a material surface to do work. So what type of work are we talking about? Well, essentially, it's breaking down of a liquid surface tension like water or, for instance, a paste adhesive. So if we look at hydrophobic surfaces where water sits proud, it tends to have a low surface energy. When we have a mid-level surface energy, we can attribute to the surface, we'll see the water forming in a dimpled droplet. Essentially, it'll sit somewhat proud, but not as proud as a hydrophobic structure. Then in a hydrophilic system, where there's a high energy present at the interface, we will see what is called fully wetting out or full spread. That is, the water becomes drawn into that structure. For the purposes of the rest of this presentation, I'm just going to touch on one subject matter in it, which is the SFE and how it is comprised. So surface free energy, or SFE as it will be sometimes termed, is typically comprises of 2 components, according to OWRK. Folks believe that these components are considered to be dispersive and non-polar and polar, but in OWRK's case, they believe in the term dispersive and polar because it matches up a little bit closer with the chemical functionalities. Dispersive in its form is Van der Waals forces or London dispersive forces. That's where it gets its name. And then polar are the types of bonds like ionic or hydrogen bonds. Dispersive bonds are usually weaker, but they're more ubiquitous within nature, which means we can utilize them naturally. Polar bonds tend to be induced bonds. They are stronger, but they're less common. So, taking an example of an FRP surface, its surface free energy might be illustrated as such. Excuse the fact that I'm using hands, but there's a whole agreement theme that's going to go on later on, so we need to use hands for this. So blue represents the dispersive energy that's available on the surface, and then yellow will represent the polar energies. It is very important to point out that contaminants, they essentially act as a function to block these energies. So they will sit on top of the energy, in this metaphor, close the fist, and essentially that will not be able to interact with any materials that are present above it. So if you introduce any liquids or any paste adhesives, they won't come in contact with that energy. So if we take the adhesive and do the exact same kind of metaphorical structure, and look at its surface tension when it comes to a liquid or a pseudo liquid, it could be represented as such. When many more hands, and that's important to point out, adhesives usually are quite energetic to form an agreeable bond. So we've done no pre-treatment to this surface. It is just a standard FRP surface. When the adhesive comes in contact with it, unfortunately, we've only 3 forms of agreement across the surface. So we end up with a poor bond. Thus, we can say from this that the bond is likely to fail adhesively or cause a recall of an in-service product. So if we know this information before we've even put the part out, we could have prevented at the design phase. But how? One way to reduce the likelihood of a chemical interaction or adhesive mismatch is to use a wettability envelope. Once the surface free energy of a material interface is determined, a wettability envelope can be generated. It could look like this for a virgin surface. It's quite a generous virgin surface, I will say, but it could look like this. So this approach now scientifically, or at least gives a scientific basis behind choosing one adhesive over another. So if you take an adhesive inside the envelope, it's likely to bond. If you have an adhesive outside of the envelope, it is unlikely to bond. However, there may not exist, and this is a very important point in the design phase, an adhesive that falls within the wettability envelope and has the suitable properties to meet the in-service needs of the product. So essentially, if it needs a high tensile strength or some property that no adhesive inside the envelope can achieve, well, that's where pre-treatment or surface preparations come from. So we would look to a surface preparation to improve the surface energy or energy available on the surface to work, and expand the wettability envelope so that it can work on the adhesive outside the envelope. And now the adhesive is likely to bond to the prepared surface and make it a viable option in future going forward. So what surface preparation techniques do we use to expand the wettability envelopes traditionally? Well, techniques and approaches such as traditional plasma, roughening, or peel ply have been demonstrated to do this for many decades. Traditional plasma, as illustrated here, it does the job really, really well, and it works in many applications. So there is a lot of times where traditional plasma is quite a positive application to use. However, for FRPs, the weak polymer interface remains between the adhesive and the fiber structure. It has difficulty also in removing contaminants from the surface, particularly oils. So they will be retained and cause a block to the surface free energy available. When we look at abrasion, which everybody probably here is aware of, we again see an increase of the surface free energy requirements, and plenty of adhesives are designed to match it. In fact, almost all adhesives are designed to have an increased dispersive component. However, fiber structures near the surface are interrupted, leading to residual stresses within the interface, and does lead to contamination within the surface, requiring further cleaning more often than not. And it is a very manual process. It's suitable for high volume, or it's not suitable for high volume continuous manufacturing, and massive waste generation and disposal of grit and cleaning effluent, which doesn't really match up with the future focus that we have within Europe and within the world really at the moment. Then finally, we have peel ply. It's a very effective when done right, and many specialist adhesives formulated to match it, specific sheet-based adhesives. However, the contaminants from peel ply layer and the moisture ingress are not uncommon, particularly when using the nylon-based peel ply systems. The fracture removal process can lead to issues with polymer fiber delamination and ingress. And then removal is a manual process, not suitable for high volume continuous manufacturing. And this is the reason why the aerospace industry would primarily be using peel-ply systems, and so would the rail industry. Very large areas, and so they're not concerned with rapid manufacturing. And specific waste, it's specifically bad at waste generation because 100% of peel-ply peeled from a surface will be disposed of. So essentially, it is all 100% waste. But they're effective nonetheless at times. So now that we have prepared the surface that was underneath, we've cleaned it and we've removed all of the contaminants, the altered surface might have the surface free energy as represented here. And the illustration, whilst an ideal illustration, it is here to show you what it looks like when an ideal bond occurs. You have an agreement across all of the chemistries that are available on the surface. Now, while of course this is a simple illustration of how an ideal scenario will be formed, Plasmabound CPA process has been shown to be able to tailor the surface properties to better match an adhesive's need. So we are trying with the CPA process to do exactly what you're seeing in front of you. So how does it do it? If we have to take a newly fabricated FRP material with its contaminants, just as it's been pulled straight out of the mold, Plasmabound CPA process can remove the top layer of the polymer and selectively expose some or all of the fiber structure beneath, while at the same time energizing the surface and simultaneously removing contaminants from the surface. On the top right there, you can see an epoxy system, where on the left of that image is the fibers free, and on the right, the fibers still remaining infused in the epoxy structure. It's important to point out at this point, the fibers beneath can be continuous, discontinuous, woven, unidirectional, and we've even worked with powder-based composites. Introducing a counter-adherent and a suitable paste adhesive, the new and energized interface means a better adhesive joint is achieved. And what is more, is there's a better opportunity for the energy, which of course, let's remember, mechanical bonding, the purpose is the transfer of energy across the bond joint. There's a better opportunity for energy and shear transfer across this common interface when the fibers are involved in the bond joint itself. In a nutshell, it's a fiber reinforced composite bond. So I mentioned in the previous slide that the level of removal can be tailored, exposing more or less of the fibers as required. So this is demonstrated here at 3 levels with coupon at the bottom of the slide. First, we have the virgin on the left. Then we have what we call internally the skim, or where there's a little bit of polymer removal, but minimal fiber exposure. So essentially, we're retaining the upper surface or structure, and we're just reducing the amount of weak polymer present at the interface. Then second to this is partial removal or reveal, where the fiber tips are exposed, but they're still infused in the fiber structure themselves. So they're ready to be used, utilized, or engaged in the bond joint, but they're not overly exposed. Then finally is the full reveal. And this means that the fibers are fully exposed and no polymer is present around the fiber structure. But critical is to all of these is that there is no fiber damage occurring during the treatment. They're only a successful treatment if the fiber has not been damaged. So depending on the customer's requirement, we could use any of these 3. There are levels or increments between them, obviously between skim to partial and partial to full reveal, but these will be the fundamental needs we would discuss with a customer. Sometimes the customer doesn't know what they need, but usually our engineers can work and support the customer in understanding what their needs or requirements are. So the CPA can remove material, but to further demonstrate its versatility on a range of fibers and polymer removal cases, this chart shows the virgin and CPA prepared SFE or surface free energy values before and after treatment. So again, note we went with polar was yellow and dispersive was blue earlier on. We're going to maintain that throughout this presentation. So firstly, we look at carbon fiber based FRPs. So before, we can see a dispersive surface with a little bit of polar, after a considerable increase in the polar contribution, but also in the dispersive contribution, and maximizing that surface free energy up to the limit that is determinable with a water-based goniometry system, which I won't dive into as detail. When we look at the more commodity-based polymer systems with glass fiber around them, so polyester, polyamides, polycarbonates, and polypropylenes, we can see a very similar trend as well. So lower polar, that then after treatment is considerably increased, and then also an increase in the dispersive component. In some scenarios, a considerable increase. Looking at future-focused adhesives, or sorry, substrates, such as polypropylene with flax or polypropylene with talc, which is used in the automotive industry quite a bit, these two materials do demonstrate an increase. They're not as high as the previous materials in the context of before and after. However, it's important to point out in the case of the flax, it's very difficult to do this treatment without causing damage to the flax structure. So the reason why the energization of it from a polar perspective is lower is to prevent the damage of the organic material within the flax structure. But this shows you that across the board, irrespective of the polymer and the fiber system, we can both remove the polymer system, but we can also work with different fiber structures as well underneath: carbon, glass, or flax, even bio-based fiber systems. So I've done a lot there, and I've kind of explained a lot about the background of bonding, and also a background of surface-free energy and all of the common interface requirements. So I said I'd give a bit of a quick case study for one of our customers as to how to utilize wettability envelope as well. So to demonstrate it in a useful way, I'm presenting an actual sample customer case study. So they came to us with this virgin surface. So we evaluated the surface-free energy and generated this wettability envelope. Using the customer's current preparation technique, we built the benchmark, which is what we have to compete with. And then when we evaluated essentially their adhesive, we found the surface tension to exist out here. So immediately we kind of understood the problem that we were trying to deal with. We engaged the customer, and the customer did agree with us. They were having intermittent issues where good bonding and sometimes not so good bonding was occurring. So this explained essentially why they approached us, and we understood the situation. During our trials, we created a series of CPA prepared surfaces, so first, second, third, and fourth, where we determined all four of these would be viable to cause a bond or create a bond or common interface with this adhesive, and we chose the CPA 4 to go forward to testing. The outcome of the mechanical testing was stark. So what we saw statistically was a significantly higher bond strength with the samples that were prepared under CPA compared to the benchmark material, but also the sporadic nature of the failure was considerably reduced. So the statistical significance was that essentially the customer could put this in service, be more confident that there would be a stronger bond for a longer period of time, and that more of the products would have that bond than in the case of benchmark, where some of the products may have a variability in their bond. So this was obviously music to the ears of our customer, because this is where everybody wants to go. Having a tighter spread and also a higher strength means that essentially you can be more guaranteed that your warranties aren't going to be an issue and that recalls won't be a concern. Another customer came to us actually looking to understand how long between treatment to the time that they can bond could they leave it essentially. We had previously observed that 22 days was viable on other material types, and so we do prefer to do these kind of tests specifically with customers at the time for their specific surface, because every time we do a CPA treatment, it creates a new interface. So when we evaluated the surface-free energy of our CPA prepared material for them over the course of 7 days, it was observed to remain above the threshold requirement for the customer's preferred adhesive. This is contrary to other preparation techniques, which may last only hours, some maybe half a day. So this means that essentially you can treat the part and store it. And we did not put this in any special environment anywhere around. It was simply sitting on a shelf, taken down, tested, and put back up. So this provides an opportunity for an extended window between treatment and bonding. And the way the customer was viewing this was, it meant that they could manufacture in one part of the world and maybe bond in another. And how they contained it in between is necessarily up to themselves, but essentially they saw this opportunity. Note also, the primary cause for decline is in the polar component, which is passivating over time. Essentially, the dispersive component of our treated surfaces remains throughout the 7 days relatively flat. So the decline is governed by the polar. This is a known effect, and it just means that the surface is slowly what's called passivating over time. So a theoretical approach to surface engineering is all well and good, and that's what we've kind of discussed quite a bit there. But mechanical testing is the benchmark to demonstrate a benefit, and everybody wants to see, well, what are the numbers? To further demonstrate the benefit of the CPA process, this graph shows the results of bonding of FRPs with a range of preparations. So what we have on the leftmost part here are the epoxy to glass fiber and epoxy to CF. Essentially, we were equivalent to the braided method. The reason being is the abraded method already caused substrate failure, and so did we. So no longer was the common interface the weak point of the bond joint, but it was now the substrate. When we moved into similar thermoplastic systems, this was again demonstrated. The peak-to-peak, PPS to PPS, and PEI to PEI CF systems, we may cause substrate failure in all three of these systems compared to abrasion and traditional plasma, which didn't perform as high for these particular material types and joints. And then when we moved into dissimilar material setups, where we have peak to aluminium, peak to epoxy CF, and PPS to epoxy CF, what we saw was quite interesting. With the peak carbon fiber to aluminium, no longer was the peak interface the issue, the common interface. We had treated it to a point where now the aluminium common interface was now the issue, the adhesive to aluminium interface. And actually it failed at the aluminium side, which means that now the customer will have to treat the aluminium side in order to see how high a CPA prepared peak CF system is capable of going to, something they've never had to do before. Because traditionally, in order to see any benefit from the peak CF, they just didn't even need to treat or anodize the aluminium side. They just needed to keep testing it. It never achieved a substrate or a interfacial failure with the aluminium side. In the peak to epoxy and peak to epoxy, or PPS to epoxy, which are the last two on this slide, this is quite interesting. There's actually no adhesive here, and this is the reason why we're interested in welding and other areas of joining and bonding. So the peak and the PPS CF, or carbon fiber, were the components treated in this. The epoxy CF is then cured onto the prepared peak and PPS material afterwards. And when these were tested in shear, or essentially a lap shear setup, they caused epoxy substrate failure. So the epoxy CF started to pull apart. And that is the reason why they're limited around about 18 to 20 megapascal, because it was the epoxy CF substrate that became the failure mode in these tests. So those are the lap shear tests, which are very common within the industry. But when we look at the double cantilever beam, which is more common in the aerospace industry, but is starting to become more prevalent within other industries as well, because it's an understanding of the quality of the bond and the amount of energy or toughness within that bond. On the top right, there is an illustration of a DCB where you have a pull-out block, you have a long two adherents and the adhesive down the middle, and the intent is these will pull apart and a crack will form down the middle of the adhesive or on the substrate itself. What you can see here, essentially on the left, is the calculations for the DCB joint fracture toughness. So for epoxy to epoxy, Plasmabound CPA outperforms traditional abrasion and virgin. It's not surprising it outperforms virgin, because virgin preparation is not particularly good, because there is none. But outperforming abrasion is a pretty good achievement, given that the adhesives are generally developed for this. When it comes to the epoxy to stainless steel, however, we match or equal the abraded version, and again, the virgin is lower. The reason for this is if the substrate failure in this case, or the adhesive failure in this case, occurred along the stainless steel line, and also the sudden increase in the stiffness should be taken into account the fact that it's an imbalanced DCB system, where there's an epoxy bonded to a dissimilar material, a stainless steel system. Additionally, and to give you a little bit more clarity on the epoxy to epoxy bonds that occurred on the left-hand side, these are the load displacement curves that were generated, a sample of them that were generated during testing. The untreated gave a very low or large variance, in the max load that was achievable. And abrasion, which followed, it gets a significant improvement in these groups, but still demonstrated a catastrophic failure. And what I mean by that is this sudden and very, 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 very quick decline or reduction in the strength integrity. When it comes to the CPA prepared surfaces, so basically our grouping is much tighter, but also fails more progressively. No longer is there a cliff edge failure, but there's actually this progressive over time failure. This progression failure means that there might be a forewarning that failures are going to occur in an in-service scenario. The final animation on the left kind of illustrates what we really see within the curve on the right. With the CPA prepared surfaces, cracks that propagate, they go through and then are arrested into the surface or substrate itself, and a new crack is required to be formed in order for there to be a subsequent follow-on failure. And that's this sawtooth, slow sawtooth effect. And that's demonstrated on the bottom image within actual testing at the time. In terms of our target markets, so we have the automotive industry, space industry, drones as well, primarily the delivery drones, because in-service has got to do a weight in that. And then aerospace and sports goods, essentially any market where a weight of a product impacts its in-service performance. And we're currently working with customers in each of these markets, but we're keen to understand, is there other markets that we might be relevant to? And in addition to this, also to engage or grow our market customer base in each of these markets. At this point, I'm going to hand you over to Sebastian from TPRC, and hopefully he can give you an overview of the interactions between Plasmabound and TPRC that have occurred in time.
Okay, thank you very much. And it's a pleasure for me to present the TPRC and our work together with Plasmabound to you. So just a few words on the TPRC. We were established in 2009 by four companies that were, or three companies and a university that were already thermoplastic composites enthusiasts. Together they decided to create a scientifically independent research center to advance the thermoplastic composite technologies and the knowledge that was already present, to specifically disseminate this knowledge through scientific publications, and also to provide a networking platform and bring together all these specialists. So starting with four, and by now we're 22 partners. And these partners are nicely distributed along the value chain that is active in the aerospace industry. So going from materials manufacturers to small parts structures to OEM, with the support of scientific staff coming from the University of Twente and the Saxion University of Applied Sciences. We're about 45 people, including our trainees and PhD students, and the majority of our income comes directly from our industrial partners. So they together finance our laboratory and the personnel. A quarter of our income comes from more commercially oriented projects, so bilateral projects, whereas the projects that are performed within the consortium, which we call roadmap research, those are exclusively for our sponsors. So let's have a look at the research roadmap. Forming is kind of the state of the art with thermoplastic composites, and I think most parts out of thermoplastic composites that are flying are made with stem forming. We're also investigating newer technologies like injection overmolding, insert molding, everything dedicated towards developing process simulation software that will make the process design process more efficient. Then we're moving on towards larger structures, and these days you can see very nice demonstrators of fuselages, which are large skins then stiffened with welded elements like stringers. We here focus on the material and process interaction during fiber placement, autoclave processing, welding, and multi-material joining. And something that is becoming more and more important with the growth of thermoplastic composites is recycling, sustainability, or repair of parts in production and at the end of the life cycle. And the performance of thermoplastic composites, as with other composites, depends on the processing history. So here we are trying to find a relation between process, structure, and the performance. So moving more and more from static mechanical performance to fatigue long-term performance. Polymer stability, that's the nice thing of having all these partners along the value chain. We can together find out how polymers behave during all these consecutive processing steps, going from material manufacture to maybe an autoclave cycle, welding, secondary welding step, and so on. How stable are the polymers and materials that we are using? What's the effect on the performance? And today we will have a look at some of our multi-material joining work. So we have run 2 PhD projects already on the joining of thermoplastic composites to titanium, specifically carbon PEG, through co-consolidation. So in one step, without a secondary, so an adhesive or intermediate layer, we join these 2 materials. And the performance really depends on the type of treatment. So surface treatment is very important here. We're currently investigating co-curing with thermosets. So since 1 year, we have a project in this field on our roadmap. But in the end, you really need to understand the behavior of the thermoplastic composite side, so the surface of the material, surface chemistry, the physics, the combination thereof. And for example, if you know that, you can also optimize paint adhesion, which is, for example, a theme that's becoming more and more important as we are moving thermoplastics to the outside of, for example, an aircraft. So the key here is surface preparation. It can be done mechanically, also through ultraviolet irradiation and plasma activation, as Nick already explained before me. So we're trying to activate the surface. Now we have been working with plasma together with Plasmabound on commercial projects. So first we started with say the polymer removal procedure in the CPA, where we ablated woven fabric reinforced PEEK and PPS. Now, specifically, PPS is very reactive to any other chemical substance. And here, with Plasmabound's treatment, we were able to achieve strengths from 0 to 20 for co-cured thermoset setting epoxy. Currently, we're moving towards unidirectional materials, specifically with the PEEK PEG and the low melting polyaryl acetone. And for example, we were also very successful in gluing a thermoplastic composite skin to a foam core. And that was also made possible by the treatment performed by Plasmabound. So this is all bilateral under NDA. So having developed the interest for plasma treatment, we decided to do a scoping study here, also as part of the research that we are doing here. Just looking at different plasma treatments. Also, we have been developing a course, 2-day course on joining, where next to fusion bonding, welding of thermoplastics, which is a very important topic these days with thermoplastics, but also to work on adhesive bonding, for example, and combined with plasma treatment. So that's where I will show a bit of our scoping study. So we looked at 4 treatments, so without treatment or just a small isopropanol alcohol wipe. We looked at hand sanding, atmospheric plasma treatment, just with a little pen-sized plasma, piezo brush PZ3, all done manually, and the Plasmabound CPA skim treatment, as Nick showed earlier. We then we prepared TC1225 unidirectional carbon low melting peak laminates provided by Torre. We used a epoxy film adhesive supplied by Solvay, the FM901M, and we cured that to the thermoplastic laminate using a heated press, which is piston operated, so we can apply pressure and heat the whole assembly up to 180 degrees in this case for a 1.5 hour cure time, pressure of about 3 bars. So it's a relatively quick way of co-curing materials, so no complex buildup in the autoclave, for example. Might have some disadvantages, but for a quick scoping study it worked. So we used this heat press setup with control through thermocouples. Then we cut single lab shear specimens according to ASTM D5868, including doublers. We usually prefer fracture toughness based testing, like the double cantilever beam or mandrel peel test. The double cantilever beam test was introduced by Nick earlier. But as a first scoping method, the lab shear test works very well, and people can quite easily relate to a lab shear strength. And we cut 6 specimens out of each assembly, and we used between 2 to 4 assemblies per treatment. Well, the atmospheric plasma treatment was done very shortly before application of the adhesive, say less than 15 minutes, because we know that the plasma treatment decays over time. And we sent plates to Ireland, where Plasmabound performed the CPA, and then they nicely wrapped up the laminates, sent them back. So you could say that time between treatment and application of the film adhesive was longer than 5 days, so between 5 and 10 days. These are the results. Funnily enough, with this material combination of the epoxy film adhesive and low melt peak, we already achieve a single lab shear strength of about 15 megapascals just using a solvent wipe. If you look at hand sanding, which would roughen up the surface and maybe activate the surface, it resulted in a lower shear strength. So probably we have contaminated the surface of the thermoplastic material. And then we saw that with both plasma treatments, atmospheric with the plasma pen and the CPA treatment, we were able to increase the lab shear strength to 20 megapascals. Although, say, with 24 specimens, you could argue about statistical relevance for, say, the standard deviation. We can see that the standard deviation on the CPE treated assembly was much lower. These are nice values. They confirm the results that Nick presented and our own experience that you can increase single lab shear strength from, say, 0 to 5 to 20. So from 5 to 20 by plasma treatment. It's not looking only at the lab shear strength values, but it's specifically looking at the fracture surface, which gives you more information. So we observed adhesive failure and cohesive failure and mixed mode. We did not observe substrate failure or fiber breakage. And if you look at, say, the amount of samples that failed according to one of these failure modes, we saw that all the hand-sanded specimens failed in the on the surface, there's a mixed mode with both the solvent wipe and the atmospheric plasma, and with CPA we only observed the cohesive failure. So that's a good sign. That's where we want the material to fail. So it's both low variation and a favorable fraction mode. So that looks really good and promising. We also performed a little bit of a microscopy under the DSEM electron microscope, where you can see that just as a demonstration, solvent wipe doesn't alter the surface. If we compare these to hand sanding and the skim treatment by Plasmabound, deep skim treatment, we see with hand sanding a lot of fibers breaking, and with CPA treatment we see that polymer is removed from the fibers. You can see the polymer sitting in between the fibers, and as we experienced with the deep treatment in other projects, where all of the fibers on the surface were revealed, this is something that's very good for thermoplastics, because thermoplastic polymers like PPS and the peaks, they like a bare fiber that gives the best adhesion. So normally a fiber is not finished or treated for adhesion with thermoplastic. So removing this original fiber sizing from the fiber is beneficial when you try to connect with a thermoplastic. So surface treatment is key for the advanced thermoplastic composites. We see great potential in plasma treatment for surface activation, and specifically the stability of the CPA treatment seems suitable when you have to spend longer times treating a part before it's bonded or, for example, painted. So that's good. And we are currently continuing our plasma treatment for co-curing and paint adhesion, and really trying to understand, getting up to the level of understanding as Plasmabound of the mechanisms that play a role with the specific materials that we research.
Thank you, Sebastian. Really appreciate that. And any questions in relation to that, we can answer at the end as well. So we're down to the basic point of what do we sell, really. Well, what we specifically sell within Plasmabound is a control device. At the moment, it's VPN based. And this method, or this device, it contains the optimized CPA recipe to prepare your FRPs, specifically designed for you and your company and your needs within the FRP space. It plugs into the back of a plasma generator and takes control of this unit's operation. So this is sold on a yearly license basis. And if you do not have a plasma generator, we can supply one. We have a partner company in France, which we operate with, and I believe TPRC are also engaged with. And it only requires compressed air and electricity to operate. And then finally, this then connects up, or should I say projects, to the emitters that are located at the end of a robot, and these are what perform the CPA treatment. In terms of collaboration opportunities, and I'll skim through this because I'm wary of time and I don't want to be delaying anybody here. So Plasmabound has received considerable support from the Irish government in the past, and it continues to do so, and this reaches internationally, which is quite unusual for the Irish government in regards to activities outside of Ireland. We're also HQ'd in Dublin, as I said earlier, Dublin, Ireland. So we are pursuing EU and European-based funding frameworks, and we'll be interested in collaborating in partnerships in any area that are relevant to this, particularly with the automotive aerospace industries. And we've been very fortunate to attract considerable private investment. So what I really want to get across or express in this slide is that we're looking for collaborative opportunities, particularly in areas that are niche or specific to your market needs. And where we could possibly go together to get a leverage framework, as in leverage funding, and then where what we specifically are also trying to say is that we have the money to leverage, and so we would be interested in pursuing this. So in summary, and I'd be trying to put summaries as few words as possible, poor adhesion can result in costly recalls because of the fact both from having to recall the actual devices or materials or cars, it's also from a brand perspective and how the value of your company sustains. Traditional methods are not future focused, with the exception of perhaps atmospheric plasma. Essentially, the other methods that are currently applied within the industry, they're not there. They're completely wasteful, and they don't operate quite as successfully as other technologies that are emerging. Interfacial properties play a key role in joint performance. That is what I'm trying to hit home here. CPA has positioned itself as one of these treatments that are capable of operating within the interfacial property space, being able to improve it for you and your customer or your application. But at the same time, we want to get across in this that you need to start thinking a little bit more, if you're bringing two things together, about the 3 interactions or 4 interactions or 5 interactions that will be occurring across those items. The adhesive and the tube materials at the base are not just the only things interacting, but the common interfaces are there too. And then finally, Plasmabound CPA technology. It provides a unique opportunity to improve both joint performance as demonstrated with the TPRC case study and all of the data that we presented in a sustainable and cost-effective way, in that we would not be as wasteful, but also at the same time, we can reduce the amount of operational steps required, automate the process, and indeed actually put your production line into a more continuous mode rather than having a more batch-based focus. So at this point, I'd like to thank you all for your time. And if you have any queries after today, please contact my colleagues, Xavier and Abhilasha. Their details are on the right-hand side of this slide here. And just to draw your attention to the events that we will be attending this year, they're along the bottom there. And now that we are happy to answer any questions, and hopefully we have time to do so. If there are any that we can't answer today or get to today, we hope we have an opportunity in the future to do so, perhaps at one of these events. And if you wish to know more about Plasmabound, my colleague will drop a link into the video in the chat, a video link to it in the chat for you to learn a little bit more about Plasmabound and what we're about. Thank you very much for your time.
Thank you very much, Nick and Sebastian, for the presentation. It's now time indeed to move to the Q&A session. We received lots of questions, and thank you, Conor, for answering already some of them. It's great. So let's move to the first question from Lyle Diobald, asking, do you have information on application rate of CPA? Area and time, thermosets and thermoplastics?
So we do, but it's so varied depending on the material type that it's difficult to say a specific area. But we would, depending on the material type that we could be working with, it can range, and depending on the application required for the customer, it can range anywhere from 50 millimeters per second, which is quite a slow treatment process, but that would be a very unique scenario, to 200 millimeters per second. And a treatment zone. And the treatment width could be anywhere between 4 to 8 millimeters wide, depending on the material type per nozzle. So as you can see behind Conor and myself there are 3 nozzle solutions. So you can do a 24 mil treatment zone in one pass at 200 millimeters per second, for instance, in some scenarios. So if they want to send us an email, I'm sure Zav will be able to fill them in a little bit more on the specifics of the different materials, so that we could actually answer their question more specific to the materials they might be working with.
Perfect. Thank you, Nick. Next questions from Scott Leemans, who is asking, since you are actually removing material from the surface with CAP, where does that material go and what hazards, if any, does it produce? What sort of abatement and PPE are required?
Yes, so this is a good question. So it depends on what's contained in it. So for traditional epoxy systems, we tend to see that they're just gasified and essentially they go out by extraction. But with filled or any composite systems or fiber reinforced systems that might have, say, talc or anything like that, the particulate matter might become suspended if there's a large removal. We tend to try and avoid that and move towards a skim function if we're doing that. But to answer the direct, if there's hard ceramic materials in it, it will become gasified potentially. And so we would have an extraction system or a hood system that will be above the plasma treatment, but this is normal with plasma anyway. And then traditionally, when it comes to the abatement or the PPE, internally, because we're an R&D lab, we would use masks, but externally in the operations generally, and with a good extraction system, you wouldn't require such PPE. I hope that kind of answers the question, but it's a difficult one again to answer. It's if there's particulate in it that we can't treat and remove or sublimate, that particulate stays as a particulate. And in those scenarios, we would tend to advise a skim.
Thank you for this answer. Next question from Kartik. Were some spectroscopic studies conducted, and do they correlate well with the outcomes of SFE studies?
So that's Kartik from University of Limerick, I believe.
Yes.
Yeah, so spectroscopic studies, we didn't carry out direct SIMS or anything. We carried out FTIR to evaluate the surfaces, but we wouldn't have been able to correlate back to SFE from those. The resolution wouldn't have been high enough. So the answer to that is no, we haven't. Very interested to talk to UL on that subject matter, though.
Okay, the next question is from Ben Amouda Chokri, asking what is the difference between CPA and plasma with chem modification?
Good question. How would I describe that? There isn't a major difference between the two in terms of traditional plasma. It's more to do with how you apply the plasma and how you drive the plasma generator, which with CPA. So there isn't a change in the chemistry. We're not using any special gases on the surface, and I hope this is answering the question. So there is no special gas within the plasma. If you had an atmospheric compressed air plasma system over there, and you have our system sitting beside them, they have the exact same feed input. So there isn't any difference in that way, but it's more to do with how you generate the plasma plume and how the plasma plume looks during the treatments. The chemistry is not being fully evaluated. I did use optical emission spectroscopy to evaluate the plume itself, and there were higher energies. I can't specifically remember it off the top of my head, but there were higher species within the plume than ordinary atmospheric plasma would observe, but I cannot remember them off the top of my head. So I've tried to answer the question from both sides there, chemistries within the plume and then also the compressed air nature of it as well. I hope that answers your question, Ben.
Thank you. Another question from Scott Leemans. Are you able to tailor the mix of chemical bond sites on the surface, not just the mix of polar to dispersive, but the mix of polar sites like amine, hydroxyl, etc., on the surface to best match the chemistry of the adhesive used in the bond? So
this is a really good question, and this is perhaps where Ben was going as well. So if we were to use a gas within our plume, a side gas or a secondary gas, we could preferentially create particular groups or sites on top of the surface. We have not moved into that range, Scott, but we do intend in the next generation of this technology to move into that space in time. Yes, we have applied other gases to confirm that is capable and we're operable in that area, but it has not been rolled out on a customer level. We're specifically, I guess, Scott, we're specifically targeting customers with easy to work with adhesives at this particular moment, like a standard epoxy system or something like that.
Okay, thank you, Nick. Another question from Rick Neff. Can you explain more about how plasma interacts with the composite to remove the resin and not the fiber?
So this is more to do with the sublimation energies that are required. So every material has a sublimation energy or an energy required in order to break down its chemical bonding or chemical structure. as it happens, most polymers have a lower sublimation energy than carbon fiber systems or any ceramic systems. That's the reason why ceramic-based or carbon fiber-based or glass-based systems tend to be quite resilient in terms of chemistries or impacts from, not mechanical impacts, but impacts from the likes of plasma. So in that scenario, we're essentially just using the difference or disparity between the two. We know that we can keep the energy high enough that it'll sublimate the polymer, but not high enough to sublimate or damage the carbon fiber system. That's why I would say that if you ever see damage on the fiber system, we've failed in the CPA process.
And a very last question we just received from Sébastien Lejeune. If we glue the part, for example, 5 days after treatment, do we need to do something on the surface, cleaning, for example? Do we pollute the surface if we touch the surface with hand, for example?
Okay, so yes, you will pollute the surface if you touch it with your hand. So it's unfortunately a case of, yeah, as soon as you put your finger on it, essentially you are going to pollute the surface. We haven't managed to create a hydrophobic, hydrophilic system or oleophobic hydrophilic system, although whoever does will be a billionaire. So yeah, if you do manage, or if you do put your finger on it, yeah, it will cause an effect. So when we're doing our longevity testing or our shelf life testing, which we actually literally put it on a shelf, so didn't even realize that parallel. We would typically put on a zone on the side of our panels where the fingers or hands can go, and that surface free energy will never be evaluated on that. So we are doing a semi-ideal scenario to assess these 5 days. So you wouldn't need to clean it, though. We have done nothing special with them. They have just sat on our shelves, so we wouldn't typically clean them afterwards if we were doing any bonding. In fact, I think recleaning them would probably cause us a problem more than a benefit, because we're a higher energy than, say, most solvents would be. So essentially, you would be reducing the energy by doing a solvent clean.
Thank you very much, Nick. We have now come to the end of this webinar, and I want to thank everyone for joining us today, and thanks for all your questions. You have, again, Plasmabound contact details on screen with Xavier and Abhilasha. If you want to reach out to them, don't hesitate. We hope that you enjoyed the time with us and have discovered a great technology today that can be applied to your business. I also want to thank Plasmabound and all people involved for the webinar today. Thank you very much for your participation. Thank you, Nick, Conor, and Sebastian. Again, the webinar was recorded and the link will be sent to you right now, together with a link to download the presentation. And in a few days, the video will be also available on the Jack Web TV at gccomposites.tv, where you can also access all previous webinar and exclusive video contents. I want also to mention, as it is mentioned on this slide, that Plasmabound will be exhibiting at GEC World in Hall 5, booth number N80, and they will also host a conference on Wednesday, April 26th at 3:30 p.m. in the Agora 5, which is in the Hall 5. So don't miss the chance, to meet with the team during the event. Our next webinar will be organized within a month, next month on March 21st with Evonik, and the webinar will be about the next generation composite solutions with Visiomer specialty methacrylates. So as usual, you can find more information on such webinar and register for free on gccomposites.tv. Thank you again, everyone, and I hope to all see you again soon. Bye-bye.
Thank you very much. Thank you,
Nick. Thank you, Sebastian. Thank you, Conor.
Thank you.
Thank you. Thanks, Benjamin. Bye-bye.
Thank you. Bye-bye.